Okay, can you hear me?
Yes, sir.
All right, I guess it's you and me.
Um, the
Yes, sir.
Labster demo still hasn't showed up in the BSC, or not the BSC, the Chem Lab, the assignment. And I was wondering if there was problems on your end, or if it was a problem with my
Okay, hold on, let me check
end.
it out. Let me check it out. Which Chem 1 lab are you in?
2045.
Which sec,
Let me see.
what section?
It's loading. 1 second.
Okay. Section 1, oh, I think you're in section 40 if I'm not mistaken.
Possibly. I can't.
Let
My
me check.
Wi-Fi is slow this morning, so I'm having a hard time.
Yeah, everything is slow. I had some issues this morning, especially with Canvas. I don't know what happened. This morning when I signed on to Canvas, I saw a message saying something like too many persons trying to log on at the same time or something. I don't know exactly what, but like now it's acting real slow when I try to open this link up. Um, let me see here. You know what? Let me just continue with the class and then I'll come back to this later on. All right. Hello. I think you're muted. Can you hear me? Hello.
Okay, I'm good with that. I'm trying to get it to work.
Okay. All right. Let me just continue with the class and then we'll deal with that later on. All right.
Sounds good.
Okay. So let me share my screen. No, let me see. And let me scroll up a bit. Can you see my screen?
Yes.
Okay, good. All right. Now, the last time we were here, we were talking about trends in ionization energy across a period and down a group. And I may have made an error in terms of describing what happens across a period. So I'm going to start from there and move forward. All right. But basically, the general trend is as you go from left to right of any period, the ionization energy increases. All right. And one can understand that in terms of the fact that as you go from left to right of a period, the nuclear charge increases, and therefore it will have a greater pull on the surrounding electrons, and therefore it becomes more difficult to remove the electrons, and therefore more energy will be required. So we can understand that particular trend going from left to right. Going from bottom to top of any group, we can understand that trend because as you go from bottom to top of a group, the distance between the valence electron and the nucleus increases, and therefore the nucleus will have a greater attraction for the valence electron, and therefore more energy will be required to remove that valence electron. So therefore, we can understand that trend as well. Now, let me go back to the across the period trend. And what I'm going to do is refer to a diagram that's in your textbook, which I'm going to pull up. Let me see. Here, all right? So this is in your textbook. If you go to your textbook on page 329, which of course is the OpenStax text, then you'll see this diagram here, which is a better plot of the ionization energy versus the atomic number than the one that I have in the PowerPoint. So what I started to explain last time was looking at the trend going from lithium to neon, which is period 2. Why is it that beryllium has a higher ionization energy compared to boron, even though boron comes after it in that period? And a similar thing happens when you go from nitrogen to oxygen. You find that nitrogen has a slightly higher ionization energy compared to oxygen, all right? So that's what we're going to explain right now. So in order for me to explain this, I'm going to go to my writing pad here. And what this is showing you, I just drew or wrote down the electron configurations of beryllium and boron, all right, firstly. And then I'll explain.
I can't.
Oh, can you see my screen?
I can see your screen, but I don't see if you're writing anything.
Oh, okay, so that means I have to do something different. Oh gosh, let me do this and then do this. No. Okay, what am I? Oh, let me see here. What is going on? Okay. All right, let me try this here. Okay, what do you see now?
I see some writing now.
Okay, good. All right, so this is what I'm talking about. Okay, so what I'm going to do is show you the reason why boron has a lower ionization energy, first ionization energy compared to beryllium. And I may have talked about this the last time, but it doesn't hurt for me to go over this again. So if you compare these two electron configurations, you'll notice that the boron has this electron here in the 2p orbital, whereas in the case of beryllium, there are two electrons here in the 2s orbital, right? So basically when boron loses an electron, it's going to lose this electron. When beryllium loses an electron, it's going to lose one of these two electrons, all right? And when you compare these two, what you'll find is that the ionization energy of boron is less than that of beryllium. And the reason why that is so is because this electron, which is lost in the case of boron, is further away from the nucleus on average, right? That's basically the nature of the 2p orbital compared to the 2s orbital. The electrons in the 2p orbital will be further away from the nucleus on average, and therefore less energy would be required to remove that electron. In the case of the beryllium atom, these two electrons are closer to the nucleus, and therefore removing one of them would be more difficult, all right? So basically, the 2p electron in boron is easier to remove because it is further away from the nucleus compared to the 2s electrons. All right, so that's basically the explanation for the fact that boron has a lower first ionization energy compared to beryllium, all right? Now, the other trend we talked about is going from nitrogen to oxygen. And what you'll find is that in terms of the ionization energy, oxygen has a lower first ionization energy compared to nitrogen. Now, in order for us to explain this, I've drawn these electron configurations, including the electrons in 2p orbitals as in boxes, all right? And I did the same thing here in the case of oxygen. And what you'll notice is that in the case of oxygen, you have two electrons here sharing the same 2p orbital, right? And there's some repulsive force between those two electrons. So therefore, as a result, oxygen would it would be easier for oxygen to lose any one of these two electrons here compared to nitrogen losing any one of these three electrons. And that's because of the repulsive forces between the two electrons sharing the same 2p orbital. So in the case of oxygen, how should I say this? In the oxygen atom, there exists repulsive forces between the two electrons sharing the same p orbital. all right? Therefore, oxygen, therefore less energy will be required to remove one of these two electrons, all right? So that explains why oxygen has a slightly lower first ionization energy compared to nitrogen, all right? So I just thought it was important for me to explain those two trends in the second period of the periodic table in terms of how the ionization energy varies as you go from left to right. So basically, to summarize, as you go from left to right of any period, generally speaking, the first ionization energy increases, but it's not, it's general, so therefore there are certain exceptions, and I just explained those exceptions with respect to going from beryllium, from boron to beryllium, and then, well, from beryllium to boron, and then from nitrogen to oxygen. Okay, so with that said, let me, okay, what am I gonna do? Let me, new share. Okay, so I'm gonna go back to my PowerPoint here. Okay, can you see the PowerPoint?
Yes.
Okay, good, all right. I guess I'm getting the hang of this Zoom thing. All right, so let me move on now to the next slide, which talks about trends in a particular property known as electron affinity, which by definition is the energy change that occurs when an electron is added to a gaseous atom. So in other words, let me go to my pen. Okay, so in other words, if the atom is X in a gaseous state, when an electron is added, it forms X minus in a gaseous state, and delta H for that change is the electron affinity, all right? So whatever the energy change that occurs for an atom undergoing this reaction here, that's called the electron affinity, all right? And I won't go into the details as to why this is so. I'll just basically summarize the trend and basically, oh, before I move on to summarizing the trend, very important point to be made right here, and that is that the electron affinities are expressed always as negative. And the reason why that is so is because this type of reaction where an atom gains an electron is always going to be exothermic, all right? So with that said, with the trends that you'll observe in the periodic table, what you'll find is that as you go from left to right on the periodic table, the electron affinity becomes more negative, and as you go from bottom to top of any group, the electron affinity becomes more negative, all right? So those are just trends that you need to know in terms of the electron affinity. And as I said before, I won't go into any details as to why that's the case because it's a bit involved, all right? Okay, so we're going to finish up on this chapter by basically discussing certain properties of metals, nonmetals, and metalloids. I think we talked about the difference between those elements, those different categories. Metals, they tend to be shiny, they tend to have high melting points, and they tend to be good conductors of heat and electricity. Non-metals are basically the opposite of metals, generally speaking. And then you have a third minority category of elements known as metalloids, which tend to behave in some cases like metals and in other cases like non-metals, right? So as stated here, one of the important aspects of metals is that their atoms tend to have a small number of electrons in their valence shells, namely 1, 2, or 3 electrons, and they tend to lose these electrons to form positive ions, all right? So what you'll find is that in terms of metallic character, the trend is that as you go down any group, the metallic character increases, and as you go from right to left of any period, the metallic character increases, right? So basically, if you were to compare two metals and if you want to know which one is more metallic than the other, you have to look at their relative positions in the periodic table. The one that's more to the left and down in the periodic table will be more metallic, all right? There are some exceptions, of course. Hydrogen and helium, which are to the left of the periodic table, basically are non-metals. They're both gases, all right? but pretty much all other elements in the S block region are metals, all right? And of course, all the D and F block elements are metals as well. Okay, then we get to nonmetals, and they tend to have a greater number of electrons, 5 to 8 electrons in their outer shell, or I should say 4 to 8 electrons in their outer shells in most cases. And when they do form ions, they do so by gaining electrons, and the ions would be negatively charged as a result. So what you'll see in terms of the trend in the non-metallic character, it will be the opposite of what we just saw in the case of metallic character as you go across a period and upper group, right? So as you go across a period and upper group, what you'll find is that the elements will tend to be more and more metallic. The nonmetals are all in the P block region. And of course, we have the hydrogen and helium, which are in the S block region, which are also nonmetals, all right? And then we have metalloids, as we said before, and metalloids have properties of both nonmetals and metals, all right? And there are 7 metalloids, which I think I gave you a list of them earlier, so you can refer to that list if you want to be reminded of what elements are metalloids. And then this here is basically a summary of the periodic trends for different properties, all right? So it's important that you know these trends and you understand them for the most part. As I said before, I did not go into details about the electron affinity, so I won't expect you to know in details why we see those trends. But with respect to non-metallic character, metallic character, ionization energy, atomic radius, you need to know the trends as you go down a group and across a period, all right? Some general comments here about certain groups. The inert gases, which are the elements in group 8, there are 6 of them and they're listed here, and they're very stable. They do not react very much. That's why they're called inert. In fact, as far as I know, helium and neon do not react with any other elements to form any compounds. The rest of them will, but you'd have to employ very sophisticated conditions in order to ensure that these elements react with other elements to form compounds. And even when those compounds are formed, basically, if you expose them to the natural environment, they'll decompose immediately. So that's just basically the nature of these elements, all right? And the reason why these elements are all so stable is because of this statement right here. They all have a complete outer shell. In other words, a complete octet, which means 8 electrons, with the exception of neon, which has a complete duet, because in the case of helium, it has only 1 shell with 2 electrons in it, which would be the first shell, which has a maximum capacity of 2 electrons. Okay, so that's as far as inert gases are concerned. And then what this is showing you is a kind of test that you can use to determine the presence of certain metals, especially those with low first ionization energies. Basically, and this would be an experiment that I would do in a normal lab, where basically you take what we call a nichrome wire, which is basically an alloy of nickel and chromium, and you dip it in a solution containing the ion, and then you put that wire in the flame, in a Bunsen flame, and the different colors will tell you what ions are present in the solution. So as you can see here, this lilac color is due to lithium, this yellow color is due to sodium, and so on and so forth, all right? So that's basically what this is all about. And the reason why this happens is because atoms emit energy when the excited electrons fall from higher to lower energy states, and therefore they give a particular color depending on the particular element. Okay, what else? Group 7. These elements are known as halogens, and one characteristic of them is that they have a property, which is that they're good oxidizing agents, right? And if you look at the oxidizing power of these different elements, what you'll find is that the oxidizing power increases as you go up the group, right? So oxidizing power increasing as you go up that group of group 7. So therefore what that means is that fluorine is a stronger oxidizing agent than chlorine, which is a stronger oxidizing agent than bromine, which is a stronger oxidizing agent than iodine. And This is useful for making predictions of certain reactions that would take place between the halogens. So an example is shown here. Now, in this test tube here, you have a solution which contain the iodide ion, all right? And what they did here is that they bubbled some chlorine into it, so Cl2 gas. And basically what will happen is that the chlorine will oxidize the iodide to form I2, which has a purple color, all right? So the purple color that you see here is your iodine solution, right? And above here, you're going to have the chloride ion present, all right? So basically, because chlorine is a stronger oxidizing agent than iodine, that means that chlorine will oxidize iodide to form the chloride ion and iodine, and the reverse reaction will not take place, right? Iodine will not oxidize chloride to form chlorine, all right? So that's basically some properties displayed by the elements in group 7. Okay, as far as the S block elements are concerned, they tend to be very good reducing agent. So for example, potassium when added to water will react violently to form potassium hydroxide and hydrogen, right? So basically what happens is that the potassium displaces the hydrogen from the water to form the products here, right? And what you'll find is that in that group, group 1, you'll find that the reactivity increases as you go down the group, right? So sodium, lithium will react with water vigorously. Sodium will do so more vigorously, and potassium will do so very vigorously. And then when you get to the other elements down that group, they react very violently in water, depending, of course, on how much of the metal you add to the water. And the same is true for group 2A. You see that trend as well, all right? And that is what is being shown here. I think this is potassium being added to water. And let me see here. And the purple colored solution here is basically indicating that the hydroxide ion is formed. I think the indicator that they added here is phenolphthalein, which is pink in base or purple, depending on how much. And therefore, as a result, it indicates that a base is formed or hydroxide is formed as a result of that reaction. Okay, what else? Okay, so here we're going to talk about the difference between acidic, basic, and amphoteric oxides. Acidic oxides basically produces acids when added to water, such as the example shown here, sulfur trioxide, when added to water forms sulfuric acid. So acidic oxides are mostly non-metallic oxides. Sulfur trioxide, sulfur dioxide, nitrogen dioxide, these are all acidic oxides, right? When added to water, they form acid solutions. On the other hand, basic oxides, which are typically metallic oxides, when added to water form bases, all right? So magnesium oxide, for example, when added to water form magnesium hydroxide, which is also known as milk of magnesia. And the same is true for sodium oxide, potassium oxide, calcium oxide, all these group 1A, group 2A metals, especially, their hydroxides tend to form basic solutions when added to water. And then we have a third category of oxides known as amphoteric oxides. And these oxides tend to behave as acids and bases, depending on what they're reacting with, all right? And a good example of this is aluminum oxide. And if I'm not mistaken, gallium oxide is also another example of an amphoteric oxide. Okay, so that's basically it for chapter, let me do this here. For chapter 8. So what we're going to do right now is commence with chapter 9. And chapter 9 deals with the all-important topic of bonding, all right? The type of chemical bonds that exist between atoms and ions, all right? So first thing we need to talk about is the nature of a chemical bond. And fundamentally speaking, the nature of a bond, and it doesn't matter what type of chemical bond it is, the nature of a bond, a chemical bond, is that it's electrostatic, which means that it is basically a force of attraction that exists between particles of opposite charges, all right? So in the case of molecules, you have what are known as covalent bonds. And in the case of, which basically holds the atoms together, let me just say that. And in the case of ionic compounds, you have what are known as ionic bonds, which are the forces that are used to hold the ions together, all right? Okay, so just to give you a simple example, a simple model, let's look at the hydrogen molecule, which consists of 2 atoms per molecule. Each hydrogen atom has a proton and an electron. So therefore, when they come together to form the molecule, you have several forces at work. You have repulsive forces between like charges, such as here and here, and you have attractive forces between unlike charges, such as here, 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 and here, all right? Now, in order for this molecule to be stable, what will happen is that the forces of attraction between unlike charges will be greater than the forces of attraction between, repulsion between like charges, right? That makes any particular structure stable. And that is no less true for the hydrogen molecule, all right? And it turns out that if you were to remove one of these electrons right here, you're going to end up with a structure which carries a +2 charge. And it turns out that this structure here is not as stable, all right? And that's because in this particular case, the repulsive forces are greater than the attractive forces, all right? And we're going to look at that in more detail when we look at the molecular orbital theory, all right? But this is just a simple explanation for the type of forces that exist within the hydrogen molecule. Okay, so another model that is used very often to explain how covalent bonds behave and work is the model where if you have a bond connecting 2 atoms, then the model that is used is that of a spring, which represents a bond, and you have 2 balls connected at each end of the spring, right? So that's a model that is used in some cases to explain how certain covalent bonds behave. And that is a model that is used to explain this graph. So let me explain what this graph is all about. It's a plot of energy versus the distance between the atoms in the bond, right? And you'll find that you end up with this curve. And what you'll find is that there's a minimum of this curve here, where basically the bond or the molecule is most stable, right? So in the case of the hydrogen molecule, which is what is represented here, the bond distance at equilibrium is 74 picometers, and the energy of that bond here would be minus 436 kilojoules, which is the energy below the 0 mark right here in this graph. Now, if you were to force the atoms closer to each other, what will happen is that the nuclei will become closer to each other, and therefore there'll be a repulsive force between those 2 nuclei. And that corresponds to what's happening on this side of the graph here, where the energy is increasing as the bond distance or the internuclear distance decreases, all right? So that increases all the way up to, infinity, all right? Now, on the other side, if you were to pull the atoms from each other, then what will happen is that there'll be an initial resistance to that pull. And therefore, that is basically what is shown here as the bond energy increases as you increase the distance. And then it gets to a point where if the atoms are pulled away from each other far enough, basically that bond will break, and therefore there'll be no intermolecular or there'll be no interatomic forces between the 2 hydrogen atoms. So that explains what happens on this side of the plot, all right? So as I said before, this is another model that is used to explain, in this case, the energy changes as the distance between the 2 nuclei increases. And of course, this is a very simple model. And that's why quantum mechanical calculations are used to develop theoretical models which would explain this and other properties of bonds even further, all right? Okay, now let's talk about the Lewis theory of chemical bonding. So this guy, G.N. Lewis, he did some theoretical work, and he came to the conclusion that electrons, and in particular valence electrons, play a fundamental role in the formation of chemical bonds. And he discovered that when an atom forms a bond, it tends to either lose, gain, or share electrons, right? So when it forms a chemical bond, they tend to lose, gain, or share electrons. And in losing, gaining, or sharing electrons, they tend to, not in all cases, but in some cases, they tend to form electron configuration of the nearest noble gas in the periodic table, all right? And we're going to see some examples of that. And one example of this would be, well, what we're going to do first is look at what happens when you have atoms losing and gaining electrons to form ionic bonds. And then later on, we're going to look at what happens when atoms share electrons to form covalent bonds, all right? So in the formation of ionic bonds, an example is shown here. Now, what we have here in this flask, we have chlorine gas in this flask. And what this person did, whoever was doing this experiment, this person dropped a very small piece of sodium into this flask, and a violent reaction takes place between the sodium and the chlorine. And basically, this is the reaction that takes place. The reaction is Na plus Cl2 to form NaCl, right? And this is a very exothermic reaction, generates a lot of heat and light, all right? So that's basically the reaction that takes place. And ionic bonding is taking place as the product is formed, all right? Okay, so let's talk about the Lewis symbol and how that applies to what we just talked about. Now, a Lewis symbol is basically the symbol of the element with dots representing the number of valence electrons in the atom. So it's a very simple representation. So for example, as you can see here for period 2, we have the different elements here, and these are the different Lewis symbols for these elements. So lithium, you notice, has 1 dot, beryllium has 2, boron has 3, carbon has 4, etc., down to neon, which has 8. And as you can see here, the number of dots, of course, will be equal to the group numbers for these respective elements, right? So it's a very simple symbol that is used to show the number of valence electrons in an atom of an element, all right? Now it says here that when you're drawing the Lewis structures or the Lewis symbols, you try to make sure that the electrons remain unpaired if possible, all right? Let me just say that I don't hold fast to that rule, because sometimes I've seen in textbooks where they do not pair up the electrons when they can in certain textbooks. So, this is not something that I would seriously pay attention to, but you can if you want to, all right? Okay, so how are we going to use Lewis symbols to show the formation of ionic bonds? So if you remember the sodium chloride example I talked about earlier, what actually happens is that the sodium atoms will lose an electron. Each atom will lose an electron to form a sodium ion. And each chlorine atom will gain the same electron that is lost here to form the chloride ion, all right? So basically what you have is the formation of ions, which are oppositely charged, the sodium and the chlorine, or the chloride, and they form what is called an ion pair. And there's a strong attraction that exists between these oppositely charged ions. As a result, this imparts certain properties to sodium chloride like any other ionic compounds, because these strong forces results in sodium chloride having high melting points, high boiling points. They tend to be hard, all right? So those are the main properties of ionic compounds, which relates directly to the fact that you have very strong attractive forces between ions of opposite charges, all right? So this is showing you again what happens. The sodium loses an electron to the chlorine, and the result will be the formation of the ion pair sodium chloride, and the force of attraction that exists between the sodium and the chloride ion is called the ionic bond. And then if you were to look at the gross structure of sodium chloride, like in the case of any ionic compound, you have, what you'll find is a highly ordered arrangement of the ions, and that is called an ionic crystal, all right? And before we look at a pictorial representation of that, I want to show you 2 other examples of ionic compounds being formed. In the case of the formation of magnesium oxide, which is the first example, the magnesium atom will give up 2 electrons to the oxygen to form the magnesium ion and the oxide ion. And in the case of the lithium oxide formation, you have 2 lithium atoms, each giving up an electron to the oxygen atom, and you end up with your lithium oxide ions being formed. One thing I should have mentioned before, and I'm going to mention here, and you'll see this in the case of sodium chloride and in these two cases, and that is that you have an octet being formed for all the ions that are formed in the formation of these ionic compounds, all right? So as you can see here, you have 2, 4, 6, 8 electrons, and in the case of magnesium, the electron configuration of magnesium will have 2 electrons in the first shell and 8 electrons in the second shell. So it also has an octet as well. So that's what happens in the formation of ionic bonds for some compounds. This is not true for all compounds, by the way. You're going to see later on that it's not true in the case of compounds necessarily formed from transition elements. Okay, as promised, I'm going to show you this diagram, which gives you a picture of how the ions are arranged in the case of sodium chloride. So basically, this is the arrangement right here. As I said before, it's an ordered arrangement, right? Very ordered arrangement where you have what is called a unit cell, which has a certain arrangement, and that unit cell is repeated throughout the structure of what we call the crystal lattice of sodium chloride. And this is basically true for all ionic compounds. They tend to have that sort of ordered arrangement of their ions. The arrangement of the crystal of the unit cells may be different, but in terms of the fact that the system is ordered, that's what they all have in common. Okay, I think this topic will be the very last topic for discussion. Oh, what time is it? 10:08? Oh, we have time. Okay. Now, what we're going to talk about here are the type of energy changes that occurs in an ionic compound when it's formed from its elements, right? So we know that we can measure the enthalpy of formation of an ionic compound, all right? But what you need to recognize is that there are several steps involved as you go from the original elements to the formation of the ionic compound. So therefore, you know, the metal, for example, will first be atomized and then converted to ions, and then you have some other changes, and the same is true for the non-metal. So the way we deal with this is that we can draw what is known as a Born-Haber cycle that we can use to determine the different changes that takes place. And it is actually an application of Hess's law. And if you recall what Hess's law says that the enthalpy change for a reaction is independent of how many steps are involved as you go from the reactant to the product, all right? So you're gonna see how that is at work in the example that we're gonna look at. Now, the example we're gonna look at is not this one, right? I mean, we can use this one, but I want to go to your text. So let me go to the particular page in your text. So this is what you'll find in your textbook on page 337, all right? And what you're seeing here is basically an example of a Born-Haber cycle, all right? So the compound you're dealing with here is cesium fluoride. And the formula for cesium fluoride is down here, all right? Okay, so we're starting from here, all right? We have cesium, which in nature exists as a solid, and we have fluorine, which exists as a gas. So the enthalpy change as you go from the elements themselves to the final compound is given right here, minus 553.5 kilojoules per mole. So that's the enthalpy of formation, all right? As you go directly from the reactants to the products. Now, what we're going to look at are the different changes that will take place as you go from the reactants to the products. And that is seen when you follow the arrows shown here, the red arrows, all right? So the first step here, going from here to here, you'll notice that the cesium solid is converted to cesium gas, all right? We call that sublimation, right? You're going from the gaseous state to the solid state. And unfortunately, I cannot write it down here, but oh gosh, okay. Well, make a note of it that this is sublimation. And you can see that it's sublimation because the symbol here is delta HS, right? S is for sublimation, all right? So basically, this is the amount of heat that is needed to convert the cesium solid to the cesium gas. And then now to go from here to here, you'll notice that the cesium gas is converted to cesium plus gas, all right? In other words, an electron is lost from here to here. That, of course, is the first ionization energy, and the value is given here. So IE is the ionization energy, and that is equal to 375.7 kilojoules per mole, all right? So that's the energy required to basically convert the cesium gaseous atoms to the cesium gaseous ions. The next step is what we call dissociation, the energy of dissociation, where the fluorine molecule, F2, is converted to the fluorine gas, all right? Now, for one molecule of fluorine, the dissociation energy would be of a certain value, and that's why we have half here. Half of that value for one molecule is equal to 79.4, and that's because we have a half as a coefficient here in front of the fluorine in this equation, right? So basically, this is the amount of energy that is required to convert half of the fluorine molecules here, or half the moles of fluorine here, to fluorine atoms, all right? Okay, and then the next step is where the fluorine gaseous atoms are converted to the gaseous ions. In other words, we're talking about the electron affinity, all right? So the electron affinity is the energy required to convert the fluorine gaseous atoms to the fluorine gaseous ions, all right? And then the very last step, we call that the lattice energy step, basically. And the definition of the lattice energy is, I think it's given somewhere here. Let me see here. Let me see here. Lattice energy. I thought I saw it earlier today, somewhere on this page, or maybe it's a previous page. Oh, okay, it's here. It's, come on. Okay, so the lattice energy by definition of an ionic compound is the energy required to convert 1 mole of the compound into its constituent gaseous ions, all right? So that's what is being shown here, right? Now, if we go back to the diagram I showed you, the Born-Haber cycle, you'll see that going in this direction, that would be the opposite of the lattice energy, the opposite direction, because the lattice energy is the energy going from the ionic compound to the gaseous ions. So therefore, this arrow here is the negative of the lattice energy, which is minus 756.9 kilojoules, all right? So after recognizing and identifying all these different steps, then we can relate all of these to each other. Basically, this plus this plus this plus this plus this will give you the energy enthalpy of formation right here. And basically, we can use a diagram like this to calculate any one of these if we know the others, right? In most cases, it is used to calculate the lattice energy. And the reason why is because the lattice energy is basically a measure of how stable an ionic compound is, in that the larger the ionic compound, or the larger the lattice energy, the more stable the ionic compound. So the greater the magnitude of the lattice energy, then that means that the ionic compound is more stable. Okay, so that's basically how the Born-Haber cycle works. Okay, any questions about the Born-Haber cycle before we move on? Because I think it's very important that you understand this, especially when it comes to certain problem solving exercises. Any questions? Any questions? No questions?
No, sir.
Okay, all right. Okay, so let's move on. Let's see what's next. Okay, so now we're going to get into drawing the Lewis structure for simple molecules. But before we do that, give me 1 minute, or I should say a couple of minutes. I'll be right back. Hold on 1 minute, all right? Okay, I'm back. All right. So now we're going to talk about Lewis structures of molecules. We talked about the Lewis symbols of atoms, and basically we can extend that idea to showing certain representations, of molecules, all right? So we're going to look at the simplest molecule, which is hydrogen. And basically what you see here is the Lewis symbol for the hydrogen molecule. And of course, we know that the hydrogen molecule is formed as a result of the sharing of electrons between these two hydrogen atoms to get your molecular structure, all right? As you can see here, each hydrogen atom will have 2 electrons in its outer shell. So therefore, as a result, it is going to be stable, right? So basically, that's a hydrogen molecule, and we can, of course, go from here to more complex structures, and that's what we're going to do. So before we do that, however, we need to talk about some definitions. The shared pair of electrons in a molecule, we call that a bonding pair of electrons, all right? Now, we can use dots to represent the shared pair, but a more common practice is that we use a line or a dash, all right? So if you see a line or dash between 2 atoms, you should immediately understand that that represents a pair of shared electrons, all right? So for example, in the case of the hydrogen chloride molecule, this dash is indicating that you have 2 electrons being shared between the hydrogen and the chlorine atom. And going back to the hydrogen molecule example that I showed you in the previous slide, that can be simply represented by this, H dash H, right? Again, this here, that line represents a shared pair of electrons, all right? Okay, so here's another example in the case of the chlorine molecule. There are 2 representations here. They're both Lewis structures, and the purpose of this is to make a distinction between what is known as the lone pair of electrons and the bonding pairs, which we talked about earlier. So this is the chlorine molecule. As you can see, you have a pair of electrons being shared between the 2 chlorine atoms, and then each chlorine atom has 6 electrons, 3 pairs of electrons, which are not shared between the 2 atoms, right? So the bonding pair would be the pair of electrons between the 2 chlorine atoms, and the lone pairs would be the 3 pairs of electrons for each chlorine atom, all right? And of course, over here, we have a line here representing the bonding pair. And let me just say, while we're here, that there's yet another representation you can use, which I personally prefer. Another representation of the chlorine molecule Lewis structure would be Cl, Cl, and then you have lines here, 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 here. So the line being shared here, that represents the bonding pair, and then these lines here represents the lone pair or non-bonding pairs of electrons, all right? So any one of these structures or representations are legitimate. You can use any one of them that you're comfortable with, all right? Okay, so just to give you some examples of Lewis symbols or Lewis structures for molecules, we're looking here at the hydrogen compounds for the elements in group, in period 2, starting from carbon. So in the case of carbon, you'll notice that the carbon is bonded to 4 hydrogen atoms. So therefore it has 4 bonding pairs around the central carbon atom. In the case of nitrogen, it is bonded to 3 hydrogen atoms. So therefore it has 3 bonding pairs and 1 lone pair. In the case of water, the oxygen, which is a central atom, has 2 bonding pairs and 2 lone pairs. And then finally, in the case of hydrogen fluoride, this fluorine here has 1 bonding pair and 3 lone pairs of electrons, all right? So those are just some examples of different molecules and what their Lewis structures look like. And it's very important, as I said before, that you're able to make a distinction between the bonding pairs and lone pairs, because as you're going to see shortly, or maybe next class, you're going to see that this is important for determining the shapes of molecules, which is very important. The shapes of molecules basically is important because if you understand the shapes of molecules plus other concepts, then you can predict certain things like the boiling point or the melting points, whether or not they'll be high or low, and other properties as well will become relatable to the shapes of molecules. So we're going to get into that later on. Okay, so just some other types of covalent bonds that we need to talk about. There's a special type of covalent bond, which is known as coordinate covalent bonds, all right? Back in the dark ages when I was in high school, we used to call these dative bonds. I don't remember seeing that term being used anymore, but that's what they used to call them back in my day. Anyway, so basically a coordinate covalent bond or dative bond is one where one atom provides both electrons that are shared between the two atoms, all right? So an example of this would be when ammonia, which is this molecule, is bonded to H+. What happens is that this pair of electrons here will be donated to the hydrogen ion, and the result would be, the result would be the formation of this particular compound, or this particular ion, N, H, 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 with a plus charge, all right? So this is called the ammonium ion. All right? So that's an example. This bond that is formed, this bond that is formed right here, that is called the coordinate covalent bond, all right? Because this bond is formed when these two electrons are donated to this hydrogen ion right here, all right? So that's a special type of covalent bond that you need to be aware of. Okay, another thing we need to talk about is the fact that you can have what we call multiple bonding. In other words, you can have more than a pair of electrons being shared between two atoms involved in the bond. And an example is shown here in the case of carbon dioxide. In the case of the carbon dioxide molecule, you'll notice that there are two lines being shared between this carbon and this oxygen, and you have the same arrangement here. Remember, each line represents a pair of electrons, right? So each line represents a bond, which is a pair of electrons. So if you have two lines here, that represents two pairs of electrons, and we call this a double bond, and we have a double bond here, all right? The bond that is formed here between the hydrogen and chlorine is just one pair of electrons, so we call that a single bond. So we have a single bond here, we have a double bond here, and we can even have a triple bond, such as in the case of nitrogen. And you'll notice that there are three lines here, so each line represents a pair. So this is a triple bond that exists between the two nitrogen atoms, all right? And you'll notice that in each case, each atom has its octet satisfied. So for example, in the case of nitrogen, you have 2, 4, 6, 8 electrons for each nitrogen atom in its outer shell. In the case of carbon, you have 2, 4, 6, 8 electrons on the outer shell of the oxygen. And the same is true for the carbon, 2, 4, 6, 8. And the same is true for this oxygen. And in the case of HCl, even though it's not shown, the chlorine here will have 8 electrons. And of course, the hydrogen can have no more than 2 electrons on its outer shell. So it is satisfied as well. So basically, it doesn't matter if it's multiple bonding or single bonding. The aim of the atoms in these types of bonding is to end up with a stable outer shell. And let me just say that you can also have quadruple bonding, but we won't get into that. That's above our level here. But you do have situations where two atoms are connected by 8 electrons. Okay, so that's all I'm going to say about that. We won't get into any examples of that. Okay, so how do we write Lewis structures? And I think this will be the very last topic that we will be discussing, all right? Now, there are certain steps that are involved, that you need to follow in order to draw Lewis structures correctly. So I'm going to get into those steps later on, but there are just certain things I want to point out here in terms of some general trends that you'll observe when you try to draw Lewis structures. The first one has to do with hydrogen atoms. And basically, you need to recognize that hydrogen atoms, where they exist in molecules, are always terminal atoms, which means basically that hydrogen atoms will be bonded to only one atom, as you can see here in the case of this compound. So each hydrogen atom that you see here can only be bonded to one atom, all right? So that's the first thing I need to point out here. The second thing I need to point out here is that the central atom of a Lewis structure usually has the lowest electronegativity and the terminal atoms, excepting hydrogen, will generally have the higher electronegativity. So for example, in this structural arrangement for a particular molecule, for this structural arrangement for this particular molecule, you have the central carbon atom here, its electronegativity value is 2.5, and then it's surrounded by 3 other atoms whose electronegativities are greater. You have oxygen, which is 3.5, and you have chlorine, which is 3.0 here and here, all right? So when you're putting the structure together, you try to make sure that the least electronegative element is placed at the center of the arrangement, all right? Of course, as I said before, hydrogen is a notable exception because hydrogen has a relatively low electronegativity, but it cannot be at the center because, as I said before, hydrogen atoms are always terminal atoms. Okay, so let me see here. When it comes to oxyacids, the hydrogen atoms that are in the oxyacids are usually bonded to oxygens, as you can see here in the case of sulfuric acid, all right? So in the case of oxyacids, you need to make sure that the arrangement is such that the hydrogens are bonded to oxygens where possible. And then if you can draw 2 or more structural arrangements that has the valence is satisfied, the one that is more likely to be correct is the one that is more compact and symmetrical. So therefore, if you have this formula SO2F2, then the arrangement is more likely to be like this, as opposed to be this linear arrangement, all right? So that's another thing you need to take into account when you're drawing Lewis structures. Okay, so these are the steps involved when it comes to drawing Lewis structures. Now, in my opinion, I think it's best that we go straight into some examples that you can see how this works. So what I'm gonna do is first choose some examples. The first one I'm going to choose is hydrogen sulfide, all right? So what I'm going to do is get out of this and go to this and get rid of this. So as I said before, hold on, what is this here? Okay, I don't know what that is. Okay. All right, I'm not sure what's going on here. Anyway, let me continue. All right, so H2S, which is hydrogen sulfide, all right? So these are the steps that you'd go through. And please try to follow this carefully. And please stop me if you have any problems understanding what I'm saying, all right? So the first step is that we count up the valence electrons, right? Now, how do we count up the total number of valence electrons? Well, all we have to do is go to the periodic table and look up the group numbers for these elements. So if you do so for hydrogen, hydrogen is in group 1, right? But because there are 2 of them, we have to multiply this by 2, right? And in the case of sulfur, if you look up the group number of sulfur, it is 6. And therefore, what you do is add this up. 6 plus 2 gives you 8 electrons. And I like to represent these as pairs. So 8 electrons will be equal to 4 pairs, all right? So we arrange it such that the least electronegative element is in the middle, excepting hydrogen, of course. So therefore, sulfur would be in the middle, and we surround it with the hydrogens, right? So that's the arrangement.
If you're writing, we can't see it.
Oh, I'm sorry. Okay, I keep forgetting I need to, I'm sorry about that. Let me go here and go here and do this. Okay, can you see it now?
Yes.
Okay, sorry about that. All right, so let me recap. This is the formula for hydrogen sulfide, all right? So what I'm doing here is counting up the valence electrons. As I said before, you go to the periodic table and you look up the group number for the elements. If you look up the group number for hydrogen, it is 1. But because there are 2 of them here in this structure, then that means you have to multiply by 2. So 2 times 1 gives you 2, and that gives you the total number of valence electrons contributed by hydrogen. We do the same thing for the sulfur. We go to the periodic table We look up the group number of sulfur, we see that it's 6, and it's only one of it, so therefore that remains. So we add the 6 to the 2, that gives us 8 electrons, which is equal to 4 pairs. And then, as I said before, we arrange this such that the least electronegative element is placed in the middle, surrounded by the hydrogens. In fact, hydrogen would be the exception here, so therefore that's why it's placed around the sulfur. Okay, the next step is that we have to place these 4 pairs of electrons. The first placement would be bonding pairs between the central atom and the hydrogen atom here. So that's 1 pair, and we put the other pair here. All right. The next step is that we put pairs of electrons on the surrounding atoms, right? However, we cannot do that for hydrogen. Why? Because hydrogen can only have 1 pair of electrons on its outer shell, right? So that means that the remaining 2 pairs will end up on the sulfur. So we put 1 pair here and 1 pair here, and that's basically it as far as the Lewis structure of hydrogen sulfide is concerned. All right, so this would be the final answer for the Lewis structure of hydrogen sulfide. All right. Okay. Any questions about this example? Any questions? Okay, so let's do another example. What example shall we use? Okay, let's use this example of NCl3, nitrogen trichloride, all right? So the first step is that we count up the valence electrons. So if you go to the periodic table, you see that nitrogen has a group number 5. And then in the case of chlorine, it's in group 7, but we have to multiply by 3 because we have 3 of them. So this gives you 21 electrons. So therefore, the total number of valence electrons would be 26 electrons, which is equal to 13 pairs. All right. Then we put the nitrogen in the middle and surround it with the chlorine atoms. And then we put the bonding pairs as we did before. So we put, now remember, we have 13 pairs of electrons to assign, all right? So the first pair would go here, the second pair would go here, the third pair would go here. Then we start putting pairs of electrons around this other atoms, making sure that their octets are satisfied. So that means that the fourth electron will go here, 5, 6, 7, 8, 9, and then 10, 11, 12, all right? So far, we have used up 12 of the 13 pairs, all right? So the question is, at this point, where will the 13th pair go? Excuse me, and the 13th pair will go here on the nitrogen, all right? And that's basically it as far as the Lewis structure of this molecule is concerned, all right? Okay, any questions about this one? Any question? Oh, and by the way, before I move on, you'll notice that each atom has 8 electrons on its outer shell, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8 for the chlorines. And then for the nitrogen, you have 2, 4, 6, 8 electrons on the outer shell of the nitrogen atom. All right, so this will be the final answer right here. Okay, any questions about this example? Any questions? Okay, so let's do another example. Suppose you're given CBr4. Okay, so based on what we have done in the previous 2 examples, what would be your first step in this process?
Splitting it up, putting C first and seeing how many electrons are in it.
Okay, so how many valence electrons would be in carbon? Do you have the periodic table at hand? You have to look at the group number. All right, let me tell you anyway. All right, in the interest of time. So that will be 4 electrons. And then in a bromine, the valence number of electrons would be 7, and there are 4 of them. So that's 4, 7, 28, right? So we add this up, and that gives you 32 electrons, which would be equal to 16 pairs, all right? So what would be the next step? Now that we have the total number of valence electrons, what would be the next step?
You're going to build around your carbon.
Okay, so you put the carbon in the middle and you surround it with the bromine atoms, all right? Okay, and then what? Now remember, we have 16 pairs to play with, all right?
Would you double line it between your carbon and bromine?
No. You put single pairs first. 1, 2, 3, 4. We're going to get to some examples of double bonding later on, but that's not what's happening here. All right, so we have used how many pairs? We have used 1, 2, 3, 4. We have used 4, but remember, we have a total of 16. So we have 12 more pairs to assign. So where will those pairs go?
Around the bromine.
Exactly. So 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And we have used up all the pairs of electrons that we have at hand, all right? And basically that's it. That's basically the final structure of carbon tetrabromide, all right? Okay, any questions about this particular example? Any questions? Okay, so let me get out of this, go back to the PowerPoint. Let me see here. Okay. So let me talk about what is called the formal charge, right? Because this is going to be important when it comes to the multiple bonding situations that we're going to encounter. I don't think we'll have enough time to talk about that today, but definitely by next class, we'll be dealing with those examples, all right? Oh, but I need to define what formal charge is first, right? So here's the definition of formal charge. It is a difference between the number of valence electrons in a free atom and the number of electrons assigned to that atom when bonded to other atoms in a Lewis structure. All right. Now, there's a formula that you can use to calculate the formal charges of any atom in any Lewis structure. And that formula is, where shall I put it? Let me see here. Okay, let me write down the formal charge formula here. So the formal charge of an atom in a structure is equal to the group number, right, of that atom minus half the number of bonding electrons.
We can't see your screen.
Oh, I'm sorry. I keep forgetting. I keep forgetting. Okay, can you see my screen now?
Yes, sir.
Okay, sorry about that. So I was writing here, right? The formal charge. Why is this thing not behaving itself? The formal charge of an atom is equal to the group number of that atom minus half the number of bonding electrons minus the number of non-bonding electrons. In fact, let me write this out so that non-bonding electrons. All right. So this is a formula that you're going to use to calculate the formal charge of an atom in a structure. All right. And in fact, whenever you draw any Lewis structure, you should calculate the formal charges of all the atoms in that structure. All right. Now, I did not do that for the examples that we saw earlier because I already knew that the formal charges for the atoms in those structures would be 0. but I'm going to just go to one of them. Let me stop sharing here. And let me go here. Okay, so can you see my screen?
Yes, sir.
Okay, good. All right, so what I'm going to show you is how do we apply that formula to this structure that we got for this last example right here. So if I were to calculate the formal charge of bromine, all right, that would be equal to the group number of bromine, which is 7, minus half the number of bonding electrons. Now, this calculation I'm doing here is for each bromine atom. So I'm just going to focus on one bromine atom. I'm going to focus on this atom right here. So half the number of bonding electrons, we have a line here. So that represents 2 bonding electrons. And then minus half the number of non-bonding electrons, which would be 2, 4, 6, right? So when you work this out, you see that this will be equal to 0. So therefore, the charge on each of the bromine atoms would be 0 here, 0 here, 0 here, and 0 here, all right? So that's basically how we calculate the formal charge of the bromine, all right? And then we do the same thing for the carbon, and that will be equal to the group number, which is 4. That's this carbon right here, minus half the number of bonding electrons, right? So for the carbon here, you have 1, 2, 3, 4 pairs, which is 8. So half of 8 bonding electrons minus the number of non-bonding electrons. For this carbon here, there are no non-bonding electrons. So that is 0, all right? And if you work this out, you'll see that the formal charge here is 0 for the carbon, all right? So that's basically how you would use the formula to calculate the formal charges of the different atoms in a Lewis structure. And you can use this formula for the other Lewis structures that we determined earlier, and you're going to see that they're all going to be 0. Now, for future reference, that won't be the case in all cases, right? Because as you're going to see in the next examples we're going to look at in the next class, there are some situations where the formal charges for specific atoms will not be 0. And in those cases, we have to basically do some more things, take some more steps in order to get to the final answer, all right? But we won't have time to do that now because it's 10:44. So that's it basically for today. I don't know if you guys have any questions to ask. Let me see here. Let me stop sharing. But if you have no questions, that's basically it for today. So enjoy your weekend. Oh, and by the way, I promised you, what was it, a quiz, but I didn't get to it. So I definitely make sure that I'll post one up later on this evening. So please look out for that, all right? Okay, so that's it basically for today. Enjoy your weekend, and I'll see you guys on Tuesday. All right, so take care.
Can you hear me?
Yeah.
I'm in section 40 of the lab. I was seeing about the Boyle's law,
Oh,
or the assignment, the labster.
oh, okay. Let me see if I can get this. What section are you in?
Section 40.
All right, so let me see here. Assignments. Boyle's law. No, was it Boyle's law or the ideal gas? Oh, it was Boyle's law.
Gas.
Hold on. Okay. Let me do this. Hold on 1 minute. Where is it? Okay, let me see here. Okay, you should be able to see it now.
Okay, is it a Labster demo or is it an actual paper?
No, it's a Labster demo.
Okay,
Mhm.
all right, thank you, sir.
Yeah, no problem. All right, take care.